Hi, everyone. Welcome to the fourth lecture in our course on modern machine learning. And in this lecture, we're going to cover our first sort of new material building on fundamentals of linear and kernel regression. And in particular, we're going to cover some new tools that have come up in the past few decades called neural network Gaussian processes. And then more recently, work on dual activations and the benefits of overparameterization in machine learning. And I know there's a lot of jargon here, but let's try to break it down simply from what we've learned so far in linear and kernel regression. So let's just recall from last time. We studied kernel regression, which was a simple way of extending linear regression, the idea of linear regression, to a nonlinear model by first transforming the data and computing a feature map that would nonlinearly transform the data, and then applying a line of best fit. So the key idea, instead of applying a nonlinear model in terms of the parameters to the data, the idea was first nonlinearly transform data. And this was by a feature map, psi. And we spoke about psi from RD to a potentially infinite dimensional Hilbert space. And then the second part was to solve linear regression in this transformed space. Okay. So the main trick that we use to do this, and especially in the case where your where your space of transformed data was infinite dimensional, we used something called the kernel trick, and we used this notion of kernels. And this allowed us to find a minimum norm solution in the Hilbert space. And we could do this tractably. It ended up being a simple linear regression problem. But the whole idea, just to outline the steps, is you're given a kernel, which was just a map. If your samples X lie in RD, it was a map on pairs of samples, so RD cross RD, into some real value. And K had this property that we used, which was just K of X and X tilde for any X and X tilde in RD. This was just the inner product of X and X tilde after I transformed them into this Hilbert space H via the feature map. And so what did we do concretely? So the concrete steps, given a data set X, Y, to solve kernel regression, we first computed this kernel training matrix where the ijth entry of this matrix. So this is, first of all, if your data X is an R d by n. So you have n samples in d dimensions, and Y, of course, is the same 1 by n. You have n labels for this data. You compute k hat, which is an n by n matrix, and k hat of ij is just the kernel between xi and xj, between those two examples. The next step was to solve, remember we assumed the minimum norm solution was a linear combination of training samples, and we had to compute the coefficients alpha i's of that linear combination. So we just had to solve the system of equations alpha k hat equals y. And typically you would get, if you just actually invert the matrix, you would just get y alpha equals y k hat inverse. And then for prediction for any other sample, we did the following. So given any sample X, which is not in our training data, we just said the solution is this alpha times this new vector. So this k of x, capital X, lowercase x, is just a vector in Rm. And k of x, the coordinate I, is just exactly the kernel value between xi and the new sample x. So this was our simple 3 steps for solving kernel regression. And what did we do in the last lecture? Well, we abstracted away this notion of feature maps because we were thinking feature map, we don't need an explicit representation, we just need this kernel. And so we thought of just general functions that satisfied the properties that we needed for a kernel, which was just inducing a positive semi-definite kernel. And one example was the RBF, or Gaussian kernel. So we thought of things like this, where it was just the exponential function norm of x minus x tilde squared. And we just gave these abstract functions without thinking about the feature map. Of course, in the second problem set, one of the exercises asks you to think about how to construct a feature map for the space, but we'll actually go over an example of this in this lecture that arises naturally from neural networks. What I want to do in this lecture is to connect kernel regression, provide a very simple connection between kernel regression and neural networks. And in particular, the way we're going to think about it is we're going to think about a neural network as first randomly extracting features from data. So we're going to think about it from this perspective of the neural network automatically gives you a feature map. And then we're just going to solve linear regression on the feature map given by a neural network. And this is a very simple connection once you see it, but it's a good start to first understanding how neural networks can be connected to these classical methods in the first place. So before I go into that connection explicitly, I know many of you may not have seen neural networks or worked with neural networks before. So I just wanted to go over quickly a simple example of what a neural network is and how we can think about it from this linear regression perspective. So let's just review what I'm going to call one hidden layer neural networks. And I will, to save myself some time, I will usually abbreviate neural networks by NN in this course. Okay. So what exactly is a neural network and how do we train it? Well, let's again assume that we're given some samples, d by n and y in R1 by n. And if you're watching this lecture for the first time and had skipped the previous lectures, I'm using the same notation for my training data through all of the lectures. In particular, I have a big matrix X, which is d by n, and of course, X is a concatenation of n samples that looks like this. And each of them is in R. Okay. And Y, again, I'm just considering is a concatenation of real values scalars, and there's n of them. So this is always the setting I'm working with. Now, a neural network, it's going to be a function for now, one hidden layer neural network. It's going to be a function that's going to be from Rd to R, but now we need to parameterize the function. And how do we do this? Well, we're going to come up with two matrices, A, which is a 1 by k matrix for some integer, positive integer k. And I'm going to let B be a k by d matrix. And notice that the k's match there between A and B. And then I'm going to take some nonlinearity phi. And phi is just a real valued function. So it's from R to R, a single variable real valued function. And I'm going to use this. This is going to be called an element-wise function. And what that means is that if I apply phi to a matrix, I'm just applying phi to every entry of that matrix. And now my neural network, for any x, I'm just going to write it as A phi of Bx. So this is going to be my predictor. And if you work out the dimensions, so keep in mind, phi is acting element-wise on B. So phi of Bx is just going to be an Rk dimensional vector. And A is, again, a 1 by k dimensional vector. And so f of x is just a real value, which is what we want. We want it to match our labels, the dimension of the labels and y. So how do we train this thing, if we're given a parameterized model like this before for linear regression, so let's just compare. In linear regression, instead of having multiple parameters and a nonlinear function in the middle, we were just taking f of x equals w times x, where w was an R1 by. But the best part is that we can train all of these models using the same technique of gradient descent. And how does this work? Well, we will construct a loss function that's the function of all of the parameters in the neural network, which is just all the entries of A and B. And now on the training data, we again just do the usual sum. So it's going to be yi minus a phi of bx I. And now how do we minimize this? Well, to minimize this loss function, we're again going to start with some initial guesses for A and B via gradient descent. And then we'll pick a learning rate and just run the equations. So you'll have a learning rate eta. And you'll just run the equations. A at time t plus 1 is A at time t minus eta times the gradient of the loss with respect to A. And then you'll similarly have a second iteration, but now you compute the gradient with respect to the loss at B, and you run both of these equations in parallel. And so this is it. This is just gradient descent. Gradient descent. And we just run this until the loss converges to a sufficiently small value, or maybe the gradients become 0, and you'll converge to some local minima. The remarkable thing is that this is a highly non-convex problem with, for those of you that are familiar with convexity, and gradient descent actually still works quite well for this problem. But apart from that, this is just a general one hidden layer neural network. Maybe I can give you some examples of what phi looks like. These phis are typically called activation functions. So phi is typically known as an activation function. And perhaps the most common examples, well, the most common example is the ReLU, which is just phi of x equals max of 0x. And then you have, of course, many other activations. You can choose whatever you want. In this course, we'll actually cover a bunch of strange ones, like sine x. You can even have phi of x equals x squared minus 1 over root 2. So there's a lot of interesting activation functions that you can pick. Okay. So now the question is, this looks like a very complicated model. There's a lot of moving parts here. You have a nonlinearity. You have two sets of parameter matrices. How is this going to connect to kernel regression, and how can we understand what a neural network is doing? So let's actually consider the simplest case, which is just when, instead of updating, so here we have two sets of equations for gradient descent, but let's assume just that the parameters b are fixed and are never updated. So when we actually run gradient descent, we just select an initial value for b naught and just don't run this second equation. We're going to, this is called freezing the parameters b naught, and we're just updating a naught to fit the data. So the key idea as a first step is freeze parameters b and just update a. So now, why is this an interesting idea, and how will it help us understand neural networks in the context of kernels? Well, if you think about b as a fixed random value, then the whole part here, this a phi bi, is just a random fixed feature map that we're applying to our data x. And then we're just updating a linear set of weights, a. So what we've effectively done is, under this idea, we have transformed our problem into taking our data points xi, mapping them to phi of b not xi, where b naught is just a random matrix. And now we solve linear regression using these transformed features. And of course, this is exactly what we did by introducing a feature map. So this is in fact exactly kernel regression. And the kernel that we're looking at here between any 2 points x and x tilde is just the inner product of phi of b naught x and phi of b naught x tilde. And I know for now this seems like kind of a trivial connection, but there's a lot of nice things we can do here. So first of all, remember that b naught, these vectors are actually vectors in Rk. But k is an integer that we get to pick. This is the number of hidden units in our neural network. So the idea that we're going to use is we're going to appropriately scale the neural network. We're going to multiply the neural network predictions by some constant so that this inner product actually converges as k goes to infinity. So we will be able to compute explicitly a kernel corresponding to an infinite width neural network where only this last layer A is trained. So let's make that idea a bit precise. So just to make the picture visually clear, let's just review what's happening here with the neural network. So for our neural network, we had f of x equals a phi bx. What I'm actually going to do now is multiply in front by root k. And pictorially, what does this neural network look like? So let's just draw a simple figure representing our neural network. So I have some examples and some inputs x coming in here. What I'm going to want to do is consider a number of hidden units k, which is very, very large. So I'm going to take k when I multiply by b. So here I'm multiplying by b and applying phi. So here I'll have phi of bx in Rk. K is going to be a very large value. I'm thinking k goes to infinity. And then what I do is I multiply by 1 over root ka, and out here is my f of x. And now I want to understand when A is the only matrix that's trained, if B is fixed as a random matrix, what does that kernel, what does the corresponding kernel look like? Now my kernel is actually going to be a little bit different. It's going to, instead of being that phi of bx, it's going to be k of x, x tilde, is 1 over root k. Oops. 1 over root k, phi of bx. And 1 over root k, phi of b naught x, tilde. And now this is going to be 1 over k, phi of b naught x, phi of b naught x tilde. Okay, and remember again, these are in Rk. So what was the point of scaling by this mysterious factor 1 over root k? Well, the idea is that now we were able to bring a 1 over k outside. And if we write this inner product, if it's just a finite dimensional vector, this is going to be a sum of k elements. And B naught is a random matrix, so it's going to be a sum of k random elements that are drawn IID. And you're dividing by 1 over k. We're going to use the law of large numbers to tractably figure out what is this kernel as k goes to infinity. So this is the key idea. And to make this a bit more precise, this notion of where we consider neural networks where only the last layer is trained and everything else is fixed, this is called the neural network Gaussian process. And in particular, it's called a Gaussian process because we're going to sample the B naughts from an IID Gaussian distribution. Okay, so here we're given this neural network, 1 over root k, A phi of bx. Okay. Now, if you have, let's say this entries of B given by Bij are sampled IID from a standard normal distribution, then the neural network Gaussian process, which is called the NNGP, is given by the kernel. And the typical notation, unfortunately, there's a lot of sums in the computation, but historically, I've seen the Gaussian process kernel written as a sigma, so that's the notation we'll stick with in this course. And this is just going to be limit as k goes to infinity, 1 over k, phi of bx, phi of bx tilde. Okay. So now this is all still very abstract, but let's actually try to simplify what this looks like. So first of all, let's come up with a proposition that helps us evaluate what is happening in this sum here. And I'm thinking I'm going to want to have a little bit more space, but let's start with the proposition on this page. Okay. So under the setting of this definition 1, we can simplify this NNGP as follows. So it's going to look a little complicated with a lot of variables coming in. But as we'll see, it's really just a few lines of computation. So I write it as this expectation over product of phi u, phi v, where u and v are drawn from the standard normal distribution. Or sorry, not standard normal. They're drawn from a multivariate Gaussian distribution, which has a covariance matrix lambda. And here lambda is exactly given by this structure. And I think in many cases, this step kind of seems mysterious in a lot of the papers, and I hope to clarify this point now. And it really is just an aspect of law of large numbers and substituting variables appropriately. So let's make this a bit clearer. So what I'm going to do is copy this over. Oops. Let's copy, and let's prove it on the next page. Okay, so here we go with the proof. So let's just start by evaluating what this kernel actually is. So by definition 1, we had the sigma was a limit of this quantity. Okay, so remember, I keep saying this, but these are vectors in Rk. Let's actually just write down what they look like. Well, this is just going to be a sum from I equals 1 to k of the product phi of bx at coordinate I, phi of bx tilde at coordinate I. And now what is exactly the coordinate I of bx, the phi of bx? So let's just write out a quick example. So phi of bx is going to be like phi applied to a giant vector. And the first entry of this vector is just the first row of b multiplied by x. The second entry is the second row of b all the way down to the kth row of b multiplied by x. So this, because phi's are being applied element-wise, I can just move the phi in. And so I get that the I coordinate is exactly here, if I'm trying to simplify this set of equations. Let me just draw a little bounding box. So if I'm proceeding with this set of equations here, I get that this is sum I equals 1 to k phi of bi, the ith row of b times x, and the ith row of b times x tilde. Okay. But now, all of these entries of bi, keep in mind that bij was just drawn IID from a standard normal distribution. And so if I look at all of the bi's, the ith rows of b, these are all isotropic Gaussian random vectors. And what does this mean? Well, it means that the bi's are IID. This is the ith row of b. This is just a giant matrix of zeros here, a giant vector of zeros. And the covariance matrix is just the identity. It should just be the d by d identity. Okay, so now I'm summing over k random variables, so the phi of bi x and phi of bi x tilde. This quantity here is just a random variable. I'm taking k samples of this random variable, and I'm averaging it. So this is exactly law of large numbers. And so if I wanted to compute that sum, what I would do is limit as k goes to infinity, 1 over k, phi of bi x, phi of bi x tilde. This converges in probability. I'll put a P here for convergence in probability, which again is in the first lecture notes for those of you who need a refresher. But this converges to the expectation of some W drawn from a multivariate Gaussian of phi of W transpose X, phi of W transpose X tilde. Okay. So now we're getting close. So if you look at the proposition, we have an expectation here, and we also have our expectation here. And we also see that we have a phi of W transpose X, phi of W transpose X tilde, and we need a phi of U, phi of B. So here's now the best trick. Of course, we just substitute and define U and B to be the things that we want. So let U equal W transpose X, let V equals W transpose X tilde. Okay, now these are Gaussian random variables because they're a linear combination of Gaussian random variables. Their mean is still 0, so expectation of U, expectation of V equals 0. These are scalars. But now they have a covariance. And this is the thing that we need to be aware of. So these are two variables that are Gaussian. And what is their covariance structure? So the thing that I would ask you to prove in the homework, which is not so bad, is just that the covariance of U and V is exactly X transpose X tilde. And so similarly, if you look at the covariance of U and U, which is just going to be the variance here. The variance is, of course, because the means are 0. That's just the expectation of the U squared. This is going to be norm X squared. Expectation of V squared is norm X tilde V squared. And by the way, how would you actually compute this? Maybe I'll give a hint for the homework. I really think it's a simple homework exercise, but as a hint, if you just look at expectation over W of W transpose X times W transpose X, this is just the expectation of mu squared. Let me write that a little cleaner. Now, this is just going to be expectation over W, summation Wi xi, xi, I equals 1 to d squared. And now as the xi's are, they each have variance 1, and they're independent and identically distributed with mean 0. This thing is just going to be exactly the expectation of the summation I equals 1 to d Wi squared xi squared. But sorry, the Wi's have, not the xi's, the Wi's have mean 0 and variance 1 there, and they're IID samples. So then this sum is exactly summation I equals 1 to d xi squared, which is just norm of x squared. Okay. But now we're good to go, because we know what the covariance structure and the means look like. Well, what's the final result? The final result is that we conclude that sigma of x tilde in probability converges to expectation of u v drawn from normal 0 lambda 5u 5v. And then lambda, of course, is exactly what we said. It's just the covariance matrix that's computed here. It's norm of x squared, x transpose x tilde, x transpose x tilde, norm of x tilde squared. Great. So now all of this is still very abstract. Great, you know, we have this sigma, which is the neural network Gaussian process. This is our first real kernel that connects neural networks and training the last layer of neural networks and solving kernel regression. And unfortunately, in this infinite width case, we have this crazy expectation to compute. Actually, what's very nice is that the expectation has been computed for us for a number of activation functions. So here's a list of examples. So we have sigma of x tilde is expectation uv normal here, phi of u, phi of v, and it has a nice covariance structure. X transpose x tilde, x transpose x tilde, norm of x tilde squared. Okay. I'm going to write these out in these examples. First of all, if we want to compute this expectation ourselves, unfortunately, there's only a couple of ways to do this before I show you the cool trick with dual activations. The naive way to do it is to literally compute the double expectation. Of course, you have your normalizing constant here for the Gaussian. But you literally just compute this double integral from negative infinity to infinity, phi of u, phi of v, times the density of the multivariate Gaussian with mean 0 and covariance matrix lambda. So you'll have a big expectation of a bunch of terms here, du, d. Okay. And I've actually done this calculation for you in the appendix of lecture 4 notes for ReLU. And unfortunately, the original paper that computed this integral uses some complex analysis. I chose to do it again, just using U substitutions and basic elements of calculus to show that it can be done. It's unfortunately not very nice or convenient, but because many people have done this for you, usually it's just a giant lookup table to see, is the neural network Gaussian process known? So for ReLU, I'll write out the simple case where your data is living on a sphere. Well, actually, I'll show that case a little bit later. The general case looks a bit like this. It's just a function, although it looks a bit terrifying at first. It's just a function you can implement, so there's nothing too crazy to be scared about with this. So it just has a few arc cosine terms or cosine inverse terms here. And then there's a sum here with some extra terms. Okay. So if I give you a function that looks like this, remember before, we just had some simple examples of like the Gaussian kernel, which was just exponential of negative L times the difference in x and x tilde norm squared. So that seemed like a simple function, but this is also just a simple function. It's easy to code up and write down, and you can solve kernel regression with it. And the best part is it's exactly equivalent to training just the last layer of a neural network that's infinitely wide. And so you can approximate this thing by actually training wider and wider finite width networks, freezing the first layer and training only the last layer. And you'll see that it exactly matches solving kernel regression here. Okay. Of course, there's many, many other examples. It wouldn't be interesting to just have it for ReLUs, although we will work with ReLUs quite a bit in this class, also the sine function. You can also do the same thing for the sine function. And by the way, when I say ReLU, this is I'm setting phi of x equals max of 0x. And then sine of x is, of course, I'm setting phi of x equals sine x. Okay. So this one also looks a little scary, but is not so bad. So this one is just exponential norm x squared plus norm x tilde squared plus x transpose x tilde. And then minus a similar quantity. So again, still the norm x squared, x tilde squared, minus. And all of these are written out in the notes in the empirical section. Okay. And I should say that many, many more are known. You can, of course, do it for leaky ReLU. You can do it for something called the I don't know how to say this, the GALU function, which is just an approximation of the ReLU with an exponential, and so on. Of course, there's also some fun examples like the error function, so the ERF. But the point is that all of these are implemented for you, and a closed form exists. And actually, in the second week of the course, we will try working with a lot of these via the neural tangents library, which is a nice library which has combined a lot of the implementation details for computing these neural network Gaussian processes for a variety of neural network architectures and activation functions. But now let's just present maybe a simple example. Let's consider the case. Let's just do this computation in a nice, simple way for the case where your activation function is phi of z equals e to the I z. And for some z belongs to R. Okay. And this is actually called the random Fourier feature model. And usually when we talk about those inner products for computing the neural network Gaussian process, we talk about real inner products. These are over some spaces L2 of R. Now we're going to be working with that space L2 of C from the introduction to the course. And our inner product is if you have two sequences which are complex valued, recall that the inner product is just going to be the sum from I equals 0 to infinity, AI, BI conjugate. Okay. So now what is the neural network Gaussian process given by? Well, it was given by this expectation. So in probability, we have convergence to this expectation. Or remember, before writing in terms of this phi of u, phi of v, we had it in terms of these isotropic weights, and it was just phi of w transpose x, phi of w transpose x tilde. But now, because of the inner product in the complex place, we have a conjugate here. And so what does this thing simplify to? Well, let's copy it over to the other page to give ourselves a little more room. Okay. So let's just substitute in what happens with our phi of z being e to the iz. Now, phi of w transpose x is just e to the I w transpose x. Phi bar of w transpose x tilde is e to the minus I w transpose x tilde, because we had to take the conjugate. Now I can simplify this. I just group the terms together, and I factor out an I, and I'm left with this difference here. And now, because all of the entries of W are independent of each other, this is this isotropic condition here, where the covariance matrix is the identity, I can do this usual trick. Let me write it as a product first. I equals, I'll call it J equals 1 to D. Now it's just expectation over Wj drawn from a standard normal of e to the I times Wjx minus Wjx tilde. And of course, what I can do is just factor out the Wj here. So I'll write it as Wj x minus x tilde. And now things are looking a bit good for me, because if you recall from the introduction notes and the first problem set, this is the expectation. Remember, before, if we considered expectation of some x drawn from a random, let me call it z, we have some random variable drawn from a standard normal. If we try to look at e to the tz, remember we did this trick of completing the square and computing that integral. So we know how to compute such integrals. So let's just do it here. So the trick was complete the square. And this was like e to the t squared over 2, if I remember correctly. Okay, so we just do the same trick here. I write this as an integral, and now this is e to the negative wj squared over 2. There's a 1 over root 2 pi up front. And there's a negative infinity to infinity here. And then I'm adding I wj x minus x tilde. This I times x minus x tilde is playing the role of my t here. And so what am I going to do is I'm just going to add and subtract in red. I'm adding an I squared x minus x tilde squared, and I subtract an I squared x minus x tilde squared. And this is, of course, dwj. Okay. Well, then this just becomes 1 over root 2 pi, negative infinity to infinity, e power negative 1/2. So I squared is going to be negative 1. So I should end up getting negative wj minus I times x. Sorry, I missed j's in my x's here. Because of course it's a dot product over a vector. Xj tilde squared over 2. And of course, we have to take the term here outside. Okay, so this is just going to be times e power x negative xj minus x tilde j squared over 2. dwj. Perfect. And sorry, we have to take this term here outside because this is the one we didn't use to complete the square. Great. So now we have this term here, which does not depend on the integral anymore. And we just pull that out. And of course, the remaining integral, which is shown in red here, this thing is just going to be 1. Because it's an integral over a Gaussian, again, with some mean. It's a complex valued Gaussian, which is an interesting distribution for those who haven't seen it. But it's, or it has a complex mean here. But the integral is still 1. And so what are we left with here? We're just left with product, j equals 1 to d, e power negative xj minus xj tilde squared over 2. Great. So now we can actually simplify this a bit further, because now the product we just rewrite as a sum. And expanding out terms, so we'll have a negative 1/2 times the sum x1 minus x1 squared, x2 minus x2 squared, up to xd minus xd squared. Now, I hope this looks a bit familiar to all of you, although it might not at first. But this is actually just the L2 norm of a vector squared. And that vector is exactly x minus x tilde. So in conclusion, we have just proved that the NNGP for the random Fourier feature model is exactly the Gaussian kernel. So this is the RBF, and we let that L value be exactly negative. I'm sorry, L is just 1/2. And so for those of you who had already started on the, or actually, for those of you who did the second problem set, there was a question asking for a feature map for the Gaussian kernel. Here we just have a feature map in the space small little L2 of C. So we have a complex valued feature map, which gives rise to the Gaussian kernel, which is a pretty neat result. And I know the derivation seems a little tricky at first, but it really is a standard computation in terms of computing expectations with an exponential function. It's really just very similar to the examples that we had in class. But I encourage everyone to go through it once more on their own in the notes. I think it really is an insightful derivation. Okay. So now, for the next part, now that we've seen some examples of the neural network Gaussian process, it's useful to note that there is a giant theory behind this, which is called the theory of dual activations. And so in the case, so here we'll discuss a bit briefly about dual activations. And I don't want to go into this theoretical part too much. It's written up extensively in the lecture notes. But it does involve a bit of functional analysis. And I think given the background of the students in this course, we're going to avoid this for now. But I want to go over the notation because it does, in fact, in some facts about dual activations, because it does make computations of the NNGP drastically easier. So we'll start off with a definition of what is a dual activation. So I'm just going to let phi of x from R to R be an activation function. okay? Then the dual of this activation function, dual activation of phi is given by, I'm going to denote it phi check to avoid confusion with things like the Fourier transform, but it really is a similar sort of transform. And it's a function from -1 to 1 with phi hat. This is going to look a bit familiar, but phi hat of psi is just going to be expectation UV drawn from this, again, the same multivariate Gaussian with just 2 variables, so bivariate Gaussian. And this lambda is given as follows. So it's just 1 on the diagonals and psi here. Okay, so this already immediately looks extremely similar to proposition 1 here, which was telling us a simple form for the neural network Gaussian process. But the interesting thing is that we no longer, remember in the NNGP, so in the NNGP, oops, we had lambda, which looked like norm x squared, x transpose x tilde, x transpose x tilde, norm x tilde squared. But now, if we just assume, so the key, assume your data is normalized to have norm 1. So assume your x tilde, lie on this unit sphere in d dimensions. Okay, so this just means that this notation, it just means that the norm of x tilde is 1. Then, of course, my neural network Gaussian process, sigma of x tilde, converges in probability exactly to this dual activation. And here, the psi, the variable psi, is just x transpose x tilde. So I would typically write this as phi checkmark of psi. Great. So I wanted everyone to just be aware of this notation because the dual activation is actually quite easy to compute for a large class of functions. These are called the Hermite polynomials. And for those of you who are familiar with it, the dual of the Hermite polynomial, the probabilist's Hermite polynomial. So this is just a remark. So if phi of x is the nth Hermite polynomial, phi check of psi is just psi power n. And so this is a very nice transform. And of course, this is only if the data is all normalized. Everything is good. Okay. But the main point that I wanted everyone to be aware of is that we can write the NNGP simply using the dual. We don't have to worry about all this crazy expectation notation. And the dual for many functions is actually known. It's exactly those computations we saw on the previous page. So when the data is normalized, so for example, for ReLU, we can simply write the following. And if I let this be psi, to simplify notation, you'll see that monstrous formula before for ReLU actually becomes quite nice. It's just psi times pi minus cosine inverse psi plus square root 1 minus psi squared. That's it. And actually, the formula for the sine function also becomes quite easy. This, usually there's a normalizing constant out front, but we can skip that. This is just exponential -1 plus psi minus exponential -1 minus psi. And this can usually, I usually write it in this form, but you can of course write it in terms of the sine h function. I think exactly it would be You factor out at e power -1, multiply and divide by 2, so it would be 2 over 2 over e, something like this, sine h. Okay. Great. So now there's a few key properties of dual activations that I would want people to keep in mind. And the first one, actually really the only one that I think is super important, is that the dual of the derivative, so if I take the dual first, so I compute check phi, and I take its derivative with respect to psi, this is actually the same function as if I took the derivative first and then applied the dual function. So the dual here is applied to derivative of phi. And why is this a bit useful? Well, we'll actually see in the next lecture when computing the neural tangent kernel, if you just know the dual activation for the NNGP, and you just know the neural network Gaussian process, it's extremely trivial to compute the neural tangent kernel. And I don't think this point has been made super cleanly in the papers out there today. But it is a super useful point, and definitely the neural tangent library takes immense advantage of this when computing the neural tangent kernel. Great. So this was just a little side note on dual activations, because it will clean up a lot of the notation for us going forward. I did also want to present now another empirical note. And this one is going to be a bit more involved. So let's go over this empirical discussion. Okay, and this is going to be on the benefit of overparameterization. And I'll explain what this term means. This is the benefit of overparameterization. And this will be our first sort of encounter with this. But we'll see that it is a real emerging trend in machine learning. And it's given us a lot of insight into understanding why larger and larger models do better. And also why the kernel methods that we have, connecting it with infinite width networks, why these should be some of the best models that we actually see. So what exactly do I mean by overparameterization? So in this lecture so far, here's just an overview of what we've done. We had our whole kernel regression framework. We connected kernel regression to neural networks. And the way we did this is we connected to neural networks where only the last layer of a neural network was trained. And then what we did is we understood the kernel for an infinite width neural network where only the last layer is trained. Okay. So now the natural thing to do, I think, is compare the performance of these things. So of course, we know that it's easy to actually do the infinite width, solve kernel regression for the infinite width neural network. We just use the neural network Gaussian process kernel. But we can, of course, always just train finite width neural networks, freezing the first layer. So let's just do that. So let's take a toy data set. In fact, in this case, I'm going to take the same data set that was considered in the kernel regression lecture. So I'm going to take a data set where I have two concentric circles. So one larger circle with points in red and one smaller circle with points in blue. And let's say I give the blue ones class label +1 and the red ones class label -1. And my goal is I'm given some subset of samples. So this is the true distribution. And I'm only given some training samples. So let's say I have 10 points, something like this. 10 points in red and some 10 points in blue. And they're not evenly distributed, they're kind of random. Okay, so the question is, from the data here, I want to learn the function here. And how will I do that? Well, I'm going to take neural networks. I'm going to do the same scaling that I did to get the infinite width one, but I'm just going to take k to be finite. In fact, I can just take k equals 1, 2, 3, maybe 10, and then I'm just going to keep increasing it in some large amounts. And then, of course, I can compute when k goes to infinity. I use the NNGP, and I can compute what happens. So the interesting thing is that if you have a set of test data, because we know the true distribution, we can just draw as many samples as we want. We'll just draw 10,000 samples and see the types of errors that we get with varying k. So let's just make a nice plot. And so there's two things that we want to measure here. We want to measure the mean squared error on our test data. So I'll call this the test mean squared error plot. And then we can, of course, look at accuracy. Did it not only just predict -1, -1, and 1, but how did the test accuracy look? And two things will emerge immediately. So if I plot on the y-axis here, the mean squared error on a log scale, and if I plot on the axis here, I just plot the test accuracy. Note in the notes, I plot 100% minus the accuracy, which is also called error in some literature. But just to avoid confusion, I'll just call it accuracy here. You'll see what happens is that for very small models, on this axis, I'm just going to plot k. Let me pick a different color here. Maybe I'll pick green. The initial models, which had k being very small, they incur some decent amount of error. And then you're in this traditional setting where if you pick k to be too large, initially you start to fit your training data perfectly. And so your test error starts to go up. You start to do some overfitting. And so here, if I note it, your training error, if I draw as a black dashed line, your training error will go to 0 at some point. And here people would say you're traditionally overfitting the data. And I'm going to call this the classical regime. But now there's an interesting question as to what happens when you keep increasing k. In fact, we understand what happens when you increase k to infinity. So what actually happens is that this curve remarkably comes back down and limits to the case where k goes to infinity. And so the case where k goes to infinity actually gives you the best test error for this problem. Now, because test error in this case does not necessarily track accuracy, you'll see an interesting trend with accuracy, where as the training accuracy goes down, as the training accuracy goes up to 100%, so initially it'll start, you can't perfectly fit the training data. So eventually it'll get to 100%, and it'll stay at 100% for all models. But the test accuracy also remarkably, it stays close here. There's a slight increase, but generally it starts to go down. And the general point is that the larger the model you use, the better you actually generalize. But it has a beautiful result as well, because we know that training these infinite width models is actually super easy to do in practice. It's like 3 lines of code, other than writing the kernel function. It's just solving a system exactly. So this is a phenomenon that was actually not just for kernels. We'll see it many times in the course. But this is a phenomenon called double descent. And maybe I'll write it in red here. And I encourage everyone to read the paper by Misha Belkin and his co-authors. which is cited in the lecture notes, which explains this phenomenon at a high level and actually connects it with kernels. I think a lot of you should be able to understand this paper very clearly now, including with the random Fourier feature model analysis that we did here. And we'll see that in all these cases, larger models tend to do better. Now, there's a lot of debate about whether this is 100% true in all cases. I think there are cases where sometimes you have that the classical underfitting models, which can't perfectly fit the data, so somewhere here, these models do actually perform better than very large models. But on most high dimensional data sets, there's a very clear emerging trend, like on CFAR10, a lot of work that OpenAI at Harvard did had shown that indeed larger neural networks actually tend to do better and they generalize better. And given the simplicity of this regime, you just perfectly fit data. There's no issue with optimization. Everything kind of works nicely. I don't see a reason to not do that other than the computational difficulty of using very large models. But now with kernel regression, there really is not too much of a computational difficulty. And we'll see that we can solve kernel regression in this course in several 100,000 examples to millions of examples. And so there's no reason why we shouldn't be able to use kernel regressions to get kernel models to get amazing results in practice. And that will be a theme of this course. Perfect. There is one other thing I wanted to mention regarding this peak here. So this peak will commonly occur when you fit data perfectly. You're considering interpolating models. And this will occur on the square loss that you're using to fit your data. One thing to make note, though, is where does this peak actually happen? And typically the peak happens when you're just at the capacity of fitting your data exactly. And this is usually called the interpolation threshold. And there are ways of actually removing this peak so that you just get the nice story that larger and larger models tend to do better. And one way to do this is actually to introduce some sort of regularization. Maybe you don't care about perfectly fitting your data, so you can try early stopping a neural network or early stopping kernel regression, especially with EigenPro, which all of you should have some familiarity with if you did the second problem set. So the general picture now is becoming clearer and clearer, but it's just that larger and larger models tend to do better. And so in this course, we're going to be working with infinite width models, and these should actually be really work remarkably well. Okay. So with this, we're going to conclude lecture 4. I know there was, again, a lot of technical material here, but in the homework, in the problem sets, you will have the opportunity to try coding up some of these examples and try running the neural network Gaussian process to see how it does. Of course, one question that still remains is we've only connected kernels with this sort of trivial case of training only the last layer of a neural network. I should say that in practice, this method somehow works remarkably well also, but we were interested in the case where a kernel method can actually match the performance of a neural network. And this is exactly what we will see in the next lecture with the neural tangent kernel. So definitely under certain conditions, very large and wide neural networks are equivalent. Training those things is equivalent to solving kernel regression with a specific kernel. And this will be called the neural tangent kernel, NTK. And so we'll introduce that. And we'll see that the computation of the NTK is actually quite easy from the computation of the NNGP. So this lecture did all of the hard work for the course. So as long as we understand this material, the rest of the course should just be pretty straightforward. So thank you again for joining me, and see you in the next lecture.